April 30th, 1942. Royal Air Force Duxford. Test pilot Ronald Harker settled into the cockpit of the North American Mustang Mark I, serial number AG 417. The morning air was cool across the Cambridgeshire aerodrome as he ran through the pre-flight checks. His fingers moved across the instrument panel with practiced efficiency. Throttle open 1 inch, mixture control in idle cutoff, propeller control in increased RPM, supercharger switch in automatic. The Allison V 1710 engine caught on the third blade, coughing blue smoke before settling into a steady rumble. Harker taxied to the runway, advanced the throttle, and felt the Mustang surge forward. The aircraft lifted cleanly, climbing through 1,000 feet, then 2,000. The controls were responsive. The visibility was excellent. Everything about the Mustang felt right. Until Harker pushed it higher. At 15,000 feet, the performance began to deteriorate. At 18,000 feet, the Mustang felt sluggish, as though invisible hands were dragging against the fuselage. At 20,000 feet, the aircraft that had been so impressive at lower altitudes had become mediocre, outclassed by German fighters that operated routinely at these heights. Harker brought the Mustang back to Duxford and climbed out of the cockpit. He had flown hundreds of aircraft over the previous decade as Rolls-Royce's senior liaison test pilot. He understood engines. He understood what made fighters effective. And he had just flown an aircraft with extraordinary potential that was being crippled by an inadequate power plant. The next day, May 1st, 1942, Harker sat down and wrote a memo that would change the course of aerial warfare. This aircraft could prove itself a formidable low and medium altitude fighter, he wrote. The point which strikes me is that with a powerful and good engine, like the Merlin 61, its performance could be outstanding. That suggestion, written in careful longhand on company letterhead, represented the collision of two separate engineering achievements. North American aviation had created an airframe with aerodynamic efficiency beyond anything previously achieved, and 90 miles north at Rolls-Royce's facility in Derby, a mathematician named Stanley Hooker had transformed the Merlin engine into something German, engineers considered impossible. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The story of how a supercharger changed the war begins not with the Mustang, but with a young mathematician who arrived at Rolls-Royce in January 1938. Stanley George Hooker had trained at Oxford in pure mathematics, earning his doctorate in fluid dynamics. He was, by his own later admission, not much of an engineer. When Ernest Hives, Rolls-Royce General Works Manager, looked at Hooker's qualifications during the job interview, he reportedly quipped, "Not much of an engineer, are you?" The comment would later become the title of Hooker's autobiography, but what Hooker lacked in traditional engineering training, he compensated for with mathematical rigor. Rolls-Royce, under Hives's leadership, was deliberately bringing in outside talent. The company had developed an excellent engine in the Merlin, but Hives recognized they needed fresh perspectives to push beyond incremental improvements. Hooker was assigned to the Supercharger test section and left to his own devices for several weeks to settle in. When Hooker examined the experimental plots of supercharger pressure, he saw immediately that large improvements were possible. The supercharger, a mechanically driven air compressor that forced additional air into the engine's cylinders, was the firm key to high-altitude performance. As aircraft climbed, air density decreased. At 30,000 feet, the air contained only 1/3 the oxygen molecules available at sea level. Without forced induction, engines lost power dramatically with altitude. The supercharger solved this by compressing thin air at altitude back to sea level density before feeding it to the engine. But the Merlin's existing supercharger design was inefficient. Hooker calculated that the intake duct geometry was wrong. The impeller blade design was suboptimal. The diffuser section, which converted the high-velocity air from the impeller into high-pressure air for the engine, was losing energy to turbulence. These were not simple problems. Supercharger design involved complex fluid dynamics, equations that most engineers approximated through trial and error. Hooker approached the problem through pure mathematics, calculating precisely how air would behave as it moved through each component. His first recommendations focused on improving the intake duct and redesigning the impeller. The existing side-entry supercharger forced air through a sharp bend before it reached the impeller eye. Hooker redesigned this as a central entry system, allowing air to flow smoothly into the impeller with minimal turbulence. He recalculated the impeller blade angles to extract maximum energy from the air as it accelerated outward. He redesigned the diffuser to more efficiently convert velocity into pressure. The improvements were put into production for the Merlin 45. The results were dramatic. Supercharger efficiency increased from 68% to 76%. Power output increased by approximately 30%. The Merlin 45 entered service in October 1940 in the Spitfire Mark V, which was produced in greater numbers than any other Spitfire variant. The improved supercharger gave RAF pilots the performance they needed to contest the skies over Britain during the most critical phase of the war. But Hooker understood that even this improved design had fundamental limits. A single-stage supercharger, no matter how efficient, could only compress air by a ratio of about 4:1 before the compressed air became so hot that it would cause detonation when ignited in the engine cylinders. Higher compression meant more power at altitude, but also more heat. More heat meant the fuel-air mixture would spontaneously ignite before the spark plug fired, causing destructive detonation that would destroy the engine within minutes. By 1941, Hooker had calculated that refining the existing single-stage supercharger would yield only marginal additional improvements. What was needed was a fundamentally new approach. The solution, Hooker realized, was to use two superchargers in series. The first stage would compress the air moderately. Then the compressed air would be cooled. Then a second supercharger would compress it again. This two-stage system could achieve compression ratios that would give the Merlin over 1,000 horsepower at 30,000 feet, more than double what a single-stage supercharger could deliver. The concept was not entirely new. Turbochargers, which used exhaust gas energy to drive a separate compressor, had been used successfully on American aircraft, like the Lockheed P-38 Lightning. But turbochargers required complex ducting to route exhaust gases to a turbine, then route compressed air back to the engine. The system added significant weight and complexity. For fighter applications, where every pound mattered and where rapid throttle response was critical, turbochargers had disadvantages that offset their benefits. Hooker's approach was different. He would place both supercharger stages in a single compact housing, driven mechanically from the engine's crankshaft. This kept the installation simple and responsive, but it created a new problem. Two stages of compression would generate extreme heat. The compressed air after the second stage might be 200 degrees Celsius or hotter. Feeding air that hot into the engine would cause instant detonation, regardless of fuel quality. Cooling the air between compression stages was essential. The standard approach would be an air-to-air intercooler, using ram air flowing through a radiator to cool the compressed charge. But in a single-seat fighter, there was no space for the large air-to-air intercooler that would be required. The ducting alone would obstruct the pilot's view and add unacceptable weight and drag. Hooker's solution was brilliant in its simplicity. He would use the engine's existing cooling system. The Merlin was liquid-cooled, with ethylene glycol coolant, circulating through passages in the engine block and cylinder heads, then flowing to a radiator where it gave up heat to the air. Hooker designed an intercooler that used this same coolant. The compressed air would flow through passages surrounded by liquid coolant. The coolant would absorb heat from the compressed air, then carry that heat to the main radiator where it would be dissipated. This air-to-liquid intercooler was compact. It fit within the engine's existing envelope. It required minimal additional plumbing, and it solved the space and weight problems that had made two-stage supercharging impractical for single-seat fighters. The brilliance of this approach was not immediately obvious to other engineers. When Hooker presented his design, some questioned whether liquid cooling would provide adequate heat transfer. American engine designers, working on similar problems, continued to focus on air-to-air intercoolers that required extensive modifications to aircraft structures, but Hooker's mathematical calculations were sound. The first test run of a two-stage supercharged Merlin occurred in March 1941. The engine was designated the Merlin 61. Initial tests confirmed that the concept worked. The two-stage supercharger, with its liquid-cooled intercooler, delivered over 1,000 horsepower at 30,000 feet. Compression ratio had increased from approximately 3.5 to 1 in the Merlin 3 to 6.5 to 1 in the Merlin 61. The power increase transformed what was possible. In the early versions of the Spitfire, powered by single-stage Merlins, the aircraft could barely reach 30,000 feet and had little power remaining for combat maneuvering at that altitude. With the Merlin 61, the Spitfire Mark 9 could fight effectively at 30,000 feet, climb faster, accelerate more rapidly, and outperform the German Focke-Wulf 190 that had been dominating RAF fighters throughout 1941 and early 1942. The timing was critical. In June 1941, when Germany launched Operation Barbarossa against the Soviet Union, the Luftwaffe had introduced the Focke-Wulf 190A. This radial engine fighter was faster than the Spitfire Mark 5 at medium and low altitudes and had better roll rate. German pilots, who had spent a year fighting Spitfires, suddenly found themselves with a superior aircraft. RAF fighter command losses increased. Pilots reported being unable to catch or escape from the 190. The Spitfire Mark 9, powered by Hooker's two-stage Merlin 61, restored qualitative parity. Test pilot Jeffrey Quill, who evaluated the Mark 9, noted that the new engine improved top speed at 30,000 feet by 70 miles per hour compared to the Mark 5. The difference between a fighter that was outclassed and a fighter that dominated was the compression ratio of the air entering the combustion chambers. But while the Spitfire's transformation was dramatic, the aircraft remained limited by its fundamental design. The Spitfire had been created in the mid-1930s as a short-range interceptor. Its wings carried enough fuel for less than 2 hours of flight. Its range was adequate for defending Britain, but inadequate for escorting bombers deep into enemy territory. What the Allies needed was a fighter that combined the Merlin's high-altitude power with much greater range. That fighter existed. It had flown for the first time in October 1940. It had exceptional aerodynamic efficiency, with a laminar flow wing that reduced drag far below what conventional designs achieved. It had been designed with range as a primary requirement, with fuel capacity for extended missions. It had proven itself in RAF service as a superb low-altitude fighter, reconnaissance aircraft. What it lacked was an engine that could deliver power at high altitude. The aircraft was the North American Mustang, and the engine it needed was Hooker's two-stage Merlin. The path to that combination began with Ronald Harker's half-hour flight on April 30th, 1942. Harker understood immediately what the Mustang represented. The airframe was more efficient than the Spitfire. The fuselage was cleaner. The laminar flow wing generated less drag. The cooling system, which used a ventral radiator scoop that actually produced slight thrust through the Meredith effect, was more sophisticated than anything else flying. But the Allison V 1710 engine that powered the Mustang had a single-stage, single-speed supercharger. It developed good power at low altitude, approximately 1,500 horsepower for war emergency power, but at 20,000 feet, power dropped to barely 1,000 horsepower. At 25,000 feet, the Allison was producing less than 800 horsepower. Against German fighters operating at these altitudes, the Allison Mustang was dangerously outclassed. Harker's memo reached the desk of Air Marshal Wilfred Freeman, the Air Member for Production and Research. Freeman had been advocating for Merlin-powered Mustangs since seeing early performance reports. The combination seemed obvious. The Mustang needed high-altitude power. The Merlin 61 provided exactly that power. Freeman authorized Rolls-Royce to convert 5 Mustang airframes to Merlin power as an experimental program. The work began at Rolls-Royce's facility at Hucknall in June 1942. The first aircraft, serial number AL 975, was fitted with a Merlin 65, a variant of the 61 optimized for slightly different altitude performance. The installation required careful engineering. The Merlin was heavier than the Allison, by approximately 300 pounds. The center of gravity shifted slightly aft. The intercooler for the two-stage supercharger required a larger radiator installation. The carburetor intake, which on the Allison fed from above the engine, had to be relocated below to accommodate the Merlin's updraft induction system. Engineers designed a new chin radiator that supplemented the ventral radiator. The combination provided adequate cooling for both the engine's coolant system and the intercooler. A four-bladed Throttle propeller, taken from Spitfire production, replaced the Mustang's original three-blade propeller. The larger propeller was needed to absorb the additional power the Merlin would produce. On October 13, 1942, Captain R.T. Shepard, Rolls-Royce's chief test pilot, climbed into AL-975 for its first flight. The aircraft, designated Mustang Mark 10, lifted from Hucknall's runway at 10:15 in the morning. Shepard climbed to altitude and began performance testing. The first hour of flight, it became clear that the Merlin Mustang was extraordinary. The aircraft reached 20,000 feet in 6 1/3 minutes, approximately two-thirds the time required by an Allison Mustang. Maximum speed at 22,000 feet exceeded 430 miles per hour. The combination of the Mustang's efficient airframe and the Merlin's high-altitude power created a fighter with performance that exceeded not just the Allison Mustang, but also the latest Spitfires, and possibly even the best German fighters. We told Chalier, Rolls-Royce's chief aerodynamic engineer at Hucknall, had calculated before the first flight that the Merlin 61 Mustang would achieve 441 miles per hour at 25,600 feet. Shepard's flight tests confirmed these predictions. The second Mustang 10 flew on November 13th and the third in December. Each demonstrated the same exceptional performance. The high-altitude engine had transformed an already excellent airframe into something unprecedented. Across the Atlantic, North American aviation had been working along parallel paths. They had known about the two-stage Merlin since late 1941. The Packard Motor Car Company, which was producing Merlins under license in the United States, had negotiated to build the two-stage version designated V1650-3, equivalent to the Merlin 68, Packard's first V1650-3. Engines would roll off production lines in mid-December 1942. On July 25, 1942, before any Merlin Mustang had flown, North American was authorized to convert two Mustang airframes to Packard Merlin power. The project was initially designated XP-78, then redesignated XP-51B. North American's engineers faced the same challenges Rolls-Royce had confronted. The heavier Merlin required moving the wing slightly forward to maintain center of gravity. The intercooler radiator was incorporated into the ventral scoop, which was made deeper and positioned with a sharp angled inlet. The carburetor intake moved from top to bottom of the nose, giving the Merlin Mustang sleeker lines than its Allison-powered predecessor. A four-bladed Hamilton standard propeller, 11 feet 2 inches in diameter, replaced the original three-blade design. On November 30th, 1942, just weeks after the first British Mustang 10 flew, North American test pilot Bob Chilton took the first XP-51B into the air from the company's Inglewood, California facility. The flight lasted 45 minutes. Chilton climbed to 29,800 feet and pushed the throttle forward. The airspeed indicator climbed past 400 miles per hour, then 420, then 440. At 29,800 feet, the XP-51B reached 441 miles per hour. The performance matched almost exactly what Rolls-Royce's Mustang 10s had achieved in England. The mathematics that Stanley Hooker had used to design the two-stage supercharger had proven accurate across 2 continents and multiple test programs. The climb rate was equally impressive. The XP-51B could climb to 20,000 feet in approximately half the time an Allison Mustang required. Rate of climb at sea level exceeded 3,000 feet per minute. Even at 25,000 feet, the Merlin Mustang was climbing at over 2,000 feet per minute. By comparison, the German Messerschmitt Bf 109G, the Luftwaffe's primary fighter in 1943, climbed at approximately 1,500 feet per minute at 25,000 feet. The decision to produce the Merlin Mustang had actually been made before either the British or American prototypes flew. In August 1942, the United States Army Air Forces ordered 400 P-51B aircraft from North American. The British ordered more than 1,000, of which 25 would eventually be delivered as the Mustang Mark III. The gamble that the Merlin Mustang would perform as predicted had proven correct. Production of the P-51B began at North American's Inglewood plant in June 1943. A second production line was established at the company's Dallas, Texas facility. Aircraft from Dallas were designated P-51C, but were identical to the B model in all significant respects. By December 1943, the first operational P-51B and C Mustangs were reaching the 8th Air Force in England. The timing was critical. The 8th Air Force's daylight bombing campaign against Germany was suffering unsustainable losses. In October 1943, more than 9% of bombers credited with attacking their targets failed to return to base. An additional 45.6% of bombers suffered battle damage. The deep penetration raids to targets like Schweinfurt and Regensburg were bleeding the bomber force faster than replacements could arrive. The problem was simple. Existing escort fighters lacked the range to accompany bombers to distant targets and return. The Republic P-47 Thunderbolt, a capable fighter, could barely reach the German border on internal fuel. With drop tanks, it could penetrate somewhat deeper, but had to turn back long before bombers reached their targets. The Luftwaffe had learned to wait beyond the range of American escorts, then attack the undefended bomber formations with devastating effectiveness. The P-51B Mustang, with its Packard V1650-3 Merlin engine and its efficient airframe, had operational range exceeding 1,600 miles with external drop tanks. This meant escort all the way to Berlin and back. It meant German fighters would face American escorts throughout the entire mission. It meant the Luftwaffe could no longer choose when and where to attack bomber formations. The first long-range escort mission using P-51B and C Mustangs occurred on December 5, 1943. Fighters from the 354th Fighter Group accompanied bombers, attacking targets in France. The Mustangs demonstrated they could stay with the bombers throughout the mission and still had fuel reserves for combat. Over the following months, more fighter groups transitioned to the P-51. By spring 1944, Merlin Mustangs were escorting every major bombing mission deep into Germany. The psychological impact on Luftwaffe pilots was profound. They had grown accustomed to a predictable pattern. American bombers would arrive escorted by Thunderbolts. The Thunderbolts would reach their range limit and turn back. Then German fighters would attack. Now the pattern had changed. The escorts stayed with the bombers throughout the mission, and these escorts, with their distinctive inline engine profile and bubble canopies in later D models, were faster at altitude than anything the Luftwaffe could field. The Messerschmitt Bf 109G had a maximum speed of approximately 400 miles per hour at altitude. The Focke-Wulf 190A could reach 408 miles per hour under optimal conditions. Against P-51B Mustangs running on 100 to 30 grade fuel, German fighters were at a modest disadvantage. When the Allies introduced 150 grade fuel in mid-1944, providing even more power at war emergency settings, the performance gap widened further. But the true advantage of the Merlin Mustang was not simply speed. It was the combination of speed, range, high altitude, performance, and quantity. By D-Day, June 6, 1944, the 8th Air Force had multiple fighter groups, equipped with Mustangs. The 9th Air Force, supporting tactical operations, also flew Mustangs. The 15th Air Force, operating from Italy, received Mustangs for escort missions against targets in southern Germany and the Balkans. German production could not match Allied numbers. In 1944, North American built approximately 9,000 P-51 Mustangs of all variants. German production of all fighter types in the same year was approximately 39,000 aircraft. But this was spread across multiple designs and included many that were obsolete or unsuited for combat against Mustangs. The Luftwaffe faced not just better aircraft, but overwhelming numbers of better aircraft. The technical specifications that made this possible traced directly to Stanley Hooker's two-stage supercharger design. The Packard V1650-7, the engine used in the P-51D variant that became the most numerous Mustang model, developed 1,490 horsepower at 3,000 RPM for standard military power. At war, emergency power settings. Using 150-grade fuel, the same engine could produce 1,720 horsepower. This power was available at altitudes where German engines were gasping for air. The two-stage supercharger compressed incoming air through the first-stage impeller, cooled it through the intercooler, compressed it again through the second-stage impeller, then fed it to the engine's cylinders at pressure that simulated sea-level conditions, even at 30,000 feet. The result was an engine that could maintain power output through an altitude range where single-stage supercharged engines lost effectiveness. The mathematics behind this performance was complex but elegant. Compression ratio multiplied through the stages. If the first stage provided compression of 2.5 to 1, and the second stage also provided 2.5 to 1, the total compression was not 5 to 1 but 6.25 to 1. The multiplicative effect of staged compression was what allowed the Merlin 60 series to achieve compression ratios that single-stage designs could not approach. The intercooler between stages was crucial. Without cooling, the second stage would be compressing air that was already heated by first-stage compression. Hot air is less dense than cool air. Compressing hot air requires more work for less pressure gain. By cooling the air between stages, Hooker ensured that the second stage operated on air nearly as dense as what the first stage received. This maximized the efficiency of each compression stage and prevented the temperature from reaching levels that would cause detonation. The liquid cooling system that made this possible was itself a marvel of compact engineering. The intercooler core, cast into the twell, supercharger housing between the two stages, contained passages through which compressed air flowed in one direction and coolant flowed in the opposite direction. This counterflow arrangement maximized heat transfer. The coolant absorbed heat from the compressed air, then flowed to the main radiator where ram air cooled it back down. The system added minimal weight because it used the engine's existing coolant pump and radiator, simply adding capacity rather than creating an entirely new cooling system. An air-to-air intercooler would have required a separate radiator, ducting to route ram air through it, and additional drag from the cooling airflow. Hooker's liquid intercooler avoided all these penalties while providing superior cooling in a more compact package. The operational impact of this engineering could be measured in many ways. Bomber loss rates, which had exceeded 9% in October 1943, dropped below 2% by summer 1944. Luftwaffe fighter losses increased dramatically as German pilots found themselves fighting American escorts that could match or exceed their performance at every altitude. The psychological effect on German pilots was severe. They were outnumbered, outperformed, and increasingly short on fuel, replacement aircraft, and experienced leaders. Hermann Göring, Reichsmarschall and commander of the Luftwaffe, reportedly stated upon seeing Mustangs escorting bombers over Berlin that he knew the war was lost. The comment reflected strategic reality. If American bombers could strike anywhere in Germany with fighter escort, then German industrial production, oil refineries, transportation networks, and military facilities were all vulnerable. The Luftwaffe could not prevent the attacks. The defenses that had worked in 1942 and early 1943 were obsolete. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The story of the Merlin Mustang is often told as the story of an airframe meeting an engine, but at its foundation, it is the story of a mathematician who understood fluid dynamics well enough to design a supercharger system that pushed the boundaries of what internal combustion engines could achieve. Stanley Hooker never flew. Combat missions. He never faced enemy fighters or anti-aircraft fire, but his work, conducted in laboratories and test cells at Derby and Hucknall, changed the balance of aerial warfare as decisively as any tactical innovation or strategic decision. The two-stage Supercharger was not Hooker's only contribution to the war effort. In 1940, he met Frank Whittle, who was struggling to get his revolutionary jet engine into production. Rover had contracts to manufacture Whittle's W.2 engine, but was failing to deliver the precision parts needed. Hooker brought the problem to Ernest Hives, who arranged for Rolls-Royce to take over jet engine production from Rover. Hooker became chief engineer of the new facility, delivering the W.2 as the Welland, which powered the earliest Gloucester Meteor jet fighters. But it was the Merlin Supercharger work that had the greatest immediate impact on the war. By mid-1944, virtually every critical Allied aircraft relied on engines that incorporated Hooker's supercharger improvements. The Spitfire Mark IX, powered by the Merlin 61, the Lancaster bomber, powered by Merlin 20s and later variants, the Mosquito, using various Merlin models, and most importantly, the P-51 Mustang, powered by Packard's license-built version of Hooker's two-stage design. The Allied victory in the air war over Europe had many causes: American industrial capacity, British determination, Soviet pressure on the Eastern Front forcing Germany to divert resources. But among the technical factors that made victory possible, the two-stage supercharged Merlin ranks among the most significant. It gave Allied aircraft performance advantages that German engineering could not match within the constraints of their synthetic fuel program and increasingly desperate strategic situation. The German pilots who first encountered Merlin-powered Mustangs in combat during the winter of 1943 and spring of 1944 did not initially understand what had changed. They knew the Americans were flying a new long-range escort fighter. They recognized the distinctive inline engine profile and the sleek fuselage. What they did not immediately grasp was that these aircraft represented a fundamental shift in the technical balance of aerial warfare. Major Heinz Baer, a Luftwaffe ace with over 200 victories, encountered P-51 Mustangs for the first time in early 1944 while flying defense missions against American bomber formations. In post-war interviews, Baer described his surprise at the Mustang's high-altitude performance. He had expected American fighters to turn back as they always had. Instead, they stayed with the bombers throughout the mission. When he attempted to attack a bomber formation, Mustangs intercepted him at altitudes where he had expected to operate without effective opposition. Baer's Messerschmitt Bf-109 G6 could reach approximately 400 miles per hour at 25,000 feet under optimal conditions. The Mustangs he encountered were faster. When he tried to disengage and dive away, the Mustangs followed. When he tried to climb for altitude advantage, the Mustangs climbed faster. The tactical options that had worked against Thunderbolts and earlier American fighters were no longer effective. The performance advantage came directly from Stanley Hooker's supercharger design. At 25,000 feet, the two-stage Merlin was producing approximately 1,390 horsepower. The single-stage supercharged Daimler-Benz DB605A engine in Baer's Messerschmitt was producing approximately 1,000 horsepower at the same altitude. The power difference of nearly 400 horsepower translated into speed differences that German pilots could not overcome through superior tactics or experience. Lieutenant Urban Drew of the 352nd Fighter Group flew P-51B Mustangs on escort missions throughout 1944. On October 7, 1944, Drew and his wingman encountered two Messerschmitt Me-262 jet fighters near Osnabrück, Germany. The Me-262 was the world's first operational jet fighter, capable of speeds exceeding 500 miles per hour. Against such aircraft, the Mustang's piston engine seemed hopelessly outclassed, but Drew understood his aircraft's capabilities. The Me-262 had speed, but its engines were unreliable, and it could not maneuver effectively at low speeds. Drew positioned himself near the Acma airfield where the jets were based, knowing they would be slow and vulnerable during takeoff and landing. When Me-262 P-62s approached to land, Drew dove on them. He shot down both jets before they could accelerate to speeds where the Mustang could not follow. The engagement demonstrated that even against technically superior aircraft, the Merlin Mustang's combination of performance, reliability, and operational flexibility provided advantages that raw speed alone could not overcome. The two-stage Supercharger allowed the Mustang to loiter at altitude, maintaining power reserves for rapid acceleration when targets appeared. German jets, for all their impressive specifications, spent most of their flight time at reduced power to conserve their limited fuel. Only during actual attack runs did they use maximum thrust. Captain Charles "Chuck" Yeager, who would later become the first pilot to break the sound barrier, flew P-51 Mustangs with the 357th Fighter Group. On October 12, 1944, Yeager shot down 5 German fighters in a single mission, achieving ace in a day status. His victims included a Messerschmitt Bf. 109, 2 Focke-Wulf 190 fighters, and 2 Messerschmitt Me 109G fighters. In his combat report, Yeager described how he used the Mustang's high-altitude performance to position above a formation of German fighters, then dove through them with enough speed to escape before they could react. He climbed back to altitude, repositioned, and attacked again. The German fighters could not match the data, Mustang's rate of climb after the diving attack. Each time Yeager climbed away, he regained altitude advantage before the German pilots could intercept him. This tactical flexibility existed because Hooker's two-stage Supercharger maintained power output through a wide altitude range. A fighter pilot could dive from 30,000 feet to 15,000 feet, accelerating to maximum speed, then climb back to 30,000 feet without losing the ability to fight. Single-stage, supercharged engines lost power dramatically as altitude increased. A German pilot who dove to low altitude and then tried to climb found his engine producing progressively less power as he climbed. The Merlin-powered Mustang pilot experienced much less power loss through the same altitude change. The statistics of the air war tell the story of this technical advantage. Between December 1943 and May 1945, P-51 Mustang pilots claimed approximately 4,950 enemy aircraft destroyed in air-to-air combat. They claimed another 4,131 destroyed on the ground during strafing attacks on German airfields. The total of over 9,000 aircraft destroyed represented a significant portion of total Luftwaffe losses during this period. Loss rates tell an equally important story. In October 1943, before Mustangs arrived in significant numbers, the 8th Air Force lost more than 9% of bombers per mission. By summer 1944, with Mustang escorts protecting every major raid, bomber loss rates had fallen below 2%. Fighter loss rates also declined, as American pilots, flying superior aircraft in overwhelming numbers, achieved kill ratios that exceeded 10-1. These numbers represented not just aircraft destroyed but also pilots killed. The Luftwaffe had entered 1944 with a cadre of highly experienced pilots, many with hundreds of hours of combat time. The attrition rate against Mustang-equipped American fighter groups was unsustainable. By autumn 1944, the average German fighter pilot reaching operational units had less than 100 hours of total flying time. Many had fewer than 50 hours. They were being sent into combat against American pilots with 300 to 500 hours of training, flying aircraft that were technically superior in virtually every performance category. Colonel Hubert Hub Zemke commanded the 356th Fighter Group, which transitioned from P-47 Thunderbolts to P-51 Mustangs in late 1944. Zemke was already an ace with more than 15 victories when he made the transition. He later described the Mustang as the most capable fighter he had flown. The combination of range, speed, high-altitude performance, and handling characteristics made it effective in every combat situation he encountered. What Zemke particularly appreciated was the Mustang's operational reliability. The Packard Merlin engine, despite its complexity with the two-stage supercharger and intercooler system, proved remarkably dependable. Mechanical failure rates were low. The liquid cooling system, which some pilots initially worried about due to its vulnerability to battle damage, proved adequately robust. A single 20mm cannon shell through a coolant line could force an emergency landing, but the same hit on any liquid-cooled engine would have similar results. The maintenance burden of the two-stage Supercharger was manageable. Ground crews learned to service the intercooler system, check the two-speed Supercharger drive mechanism, and maintain the complex induction plumbing. Spark plug life was somewhat shorter than with simpler engines due to the higher compression ratios, but this was offset by the improved combat effectiveness. Engine overhaul intervals were reasonable. The Merlin could operate reliably for hundreds of hours between major maintenance. Major George Preddy of the 352nd Fighter Group became the highest-scoring Mustang ace in the European theatre, with 26.83 confirmed victories. Flying a P-51D named Cripes A Mighty Third, Preddy exploited the Mustang's high-altitude performance to achieve multiple victories in single missions. On August 6, 1944, Preddy shot down 6 German fighters in a single engagement, the highest single mission score by any American pilot in the European theatre. Preddy described his tactics in interviews and combat reports. He would position at high altitude, typically above 25,000 feet, where the Mustang's performance advantage was greatest. German fighters attempting to attack bomber formations below had to climb through the altitude where Preddy waited. As they climbed, their single-stage supercharged engines lost power. Preddy's Merlin maintained power. He would dive on climbing German fighters, using his altitude advantage to build speed, then use that speed to climb back to altitude after the attack. The physics of this tactic were straightforward. A fighter diving from 30,000 feet to 20,000 feet converted 10,000 feet of altitude into kinetic energy. That energy translated into speed. The Mustang's clean aerodynamics meant it could reach speeds exceeding 500 miles per hour in such dives. German fighters, starting from lower altitude and climbing with engines that were losing power, could not match this performance. Preddy was killed on Christmas Day 1944, not by German fighters, but by friendly fire from American anti-aircraft artillery during a low-altitude engagement. His death illustrated the dangers of low-altitude combat, where the Mustang's high-altitude advantages were less pronounced and where ground fire posed significant threats. But his combat record demonstrated what a skilled pilot could achieve with an aircraft whose engine delivered power where it was most needed. The technical specifications that enabled these tactical advantages traced directly to decisions Stanley Hooker had made when designing the Merlin 60 series supercharger. The compression ratio of 6.5 to 1 that his two-stage system achieved was the result of careful calculation of impeller diameters, blade angles, rotational speeds, and intercooler efficiency. Each variable affected the others. Increasing compression ratio increased heat generation, which required more intercooler capacity, which added weight and complexity. Hooker's genius lay in finding the optimal balance. The Merlin 61 produced enough power at altitude to give decisive performance advantages, but not so much that reliability suffered. The intercooler was large enough to prevent detonation, but compact enough to fit within the engine's envelope. The two-speed supercharger drive allowed the engine to optimize performance for different altitude bands, but added minimal complexity compared to continuously variable systems. The contrast with German engine development was instructive. Daimler-Benz had developed excellent engines in the DB601 and 605 series. These engines were reliable and produced good power, but they relied on single-stage superchargers, some with two-speed drives, and could not match the high-altitude performance of the two-stage Merlin. German engineers had considered two-stage supercharging but had not implemented it effectively in production engines. Part of the German disadvantage came from fuel constraints. The two-stage supercharger's higher compression ratios required high-octane fuel to prevent detonation. Germany's synthetic fuel program, which converted coal into aviation gasoline through the Fischer-Tropsch process, could not produce fuel with octane ratings comparable to Allied fuels. German B4 fuel rated at approximately 91 octane on the lean mixture scale. Their premium C3 fuel was roughly equivalent to Allied 130 grade fuel, but available in far smaller quantities. Even if German engineers had designed a two-stage supercharger system comparable to Hooker's, they would have struggled to use it effectively without fuel that could withstand the higher compression ratios. This created a cascading series of limitations. Lower octane fuel meant lower permissible compression ratios. Lower compression ratios meant less power at altitude. Less power at altitude meant inferior combat performance. Inferior combat performance meant higher loss rates. Higher loss rates meant fewer experienced pilots. Fewer experienced pilots meant worse combat results, regardless of equipment quality. By contrast, the Allies had access to progressively better fuels throughout the war. 100-octane fuel became standard in 1942. 130-grade fuel, with a performance number of 130 on rich mixture, entered service in 1943. 150-grade fuel, with a performance number of 150, became available in mid-1944. Each fuel improvement allowed higher manifold pressures and more power from the same engine. The P-51D Mustang, powered by the Packard V1650-7 Merlin, could use all these fuels. On 130-grade fuel, the engine produced 1,490 horsepower at military power and 1,690 horsepower at war emergency power. On 150-grade fuel, war emergency power increased to 1,720 horsepower. The performance increase was significant. Maximum speed increased from approximately 437 miles per hour to 448 miles per hour. Climb rate improved by several hundred feet per minute. These improvements came with no modifications to the aircraft. The same Mustang flown on 130-grade fuel one day and 150-grade fuel the next day became measurably faster simply because of the fuel in its tanks. But the fuel only delivered this advantage because Hooker's supercharger design could exploit it. The two-stage compression, combined with intercooling, allowed the engine to use higher manifold pressures without detonation. Single-stage designs hit detonation limits at lower manifold pressures, even with better fuel. The Tuskegee Airmen, the African-American pilots of the 332nd Fighter Group, flew P-51 Mustangs from June 1944 through the end of the war. Based in Italy and operating with the 15th Air Force, they escorted bombers, attacking targets in southern Germany, Austria, and the Balkans. The 332nd achieved an outstanding combat record, with pilots claiming 112 enemy aircraft destroyed in air combat and approximately 150 destroyed on the ground. Lieutenant Colonel Lee Archer, one of the Tuskegee Airmen's leading aces, described the Mustang as the finest fighter he flew during the war. The combination of range, allowing missions deep into enemy territory, and high-altitude performance, allowing engagement on favorable terms, made escort missions more survivable. The 332nd became known for staying close to the bombers they protected, rarely leaving formation to chase distant targets. Their bomber loss rates were among the lowest in the theater. Captain Roscoe Brown, of the 332nd Fighter Group, shot down a Messerschmitt Me 262 jet fighter on March 24, 1945, while escorting bombers to Berlin. Brown's engagement followed a similar pattern to Urban Drew's earlier success. The Me 262 was fast in level flight, but vulnerable during landing approach. Brown positioned himself near the jet's airfield and intercepted it as it slowed for landing. The Mustang's high-altitude performance allowed Brown to maintain position at the jet's service ceiling while waiting for the moment when speed advantage became irrelevant. The final statistics of Mustang operations reveal the cumulative impact of Hooker's engineering decisions made years earlier in the Supercharger test section at Derby. Over 15,000 P-51 Mustangs of all variants were produced during the war. They equipped dozens of fighter groups across the European, Mediterranean, and Pacific theaters. They flew hundreds of thousands of sorties. They claimed nearly 5,000 enemy aircraft destroyed in air combat and thousands more destroyed on the ground. But beyond the numbers, the Merlin Mustang's impact was psychological and strategic. German fighter pilots, in late 1944, knew they were facing an opponent that was technically superior, numerically overwhelming, and operationally flexible. The knowledge that American escorts could appear anywhere at any altitude with performance advantages that could not be countered through tactics alone eroded morale and effectiveness. Hermann Goering's comment about knowing the war was lost when he saw Mustangs over Berlin reflected this strategic reality. The Luftwaffe's defensive strategy had relied on geography. Britain was within range of German fighters, but Germany's interior was not within range of British-based escorts. The Mustang eliminated this geographic advantage. Combined with the two-stage Merlin's high-altitude performance, it meant American bombers could strike any target in Germany with fighter protection throughout the mission. The bombing campaign's effectiveness increased dramatically once effective fighter escort became available. Precision daylight attacks on German synthetic fuel plants, particularly the raids on Leuna and other major facilities in May and June 1944, crippled German fuel production. Aircraft factories, ball bearing plants, transportation choke points, and communication centers all became vulnerable to attacks that the Luftwaffe could no longer prevent. By autumn 1944, Germany was rationing aviation fuel. Fighter units received priority, but even they operated under severe constraints. Training for new pilots was cut to minimal levels. Many German pilots reached combat units with barely enough flight time to handle their aircraft safely, much less fight experienced American pilots in superior machines. The technical advantages of the Mustang compounded the training disadvantages, the numerical disadvantages, and the fuel supply disadvantages to create a situation where defeat was inevitable. Stanley Hooker never visited the combat theatres to see his Supercharger design in action. He remained in England throughout the war, continuing to develop improved engine variants and beginning work on the jet engines that would power Britain's post-war aircraft. In 1943, after the two-stage Merlin had proven itself in service, Hooker turned his attention to Frank Whittle's revolutionary jet engine program. He brought the same mathematical rigor to jet engine development that he had applied to superchargers. The transition from piston engines to jets was natural for Hooker. A jet engine's compressor was essentially a multi-stage supercharger driven by a turbine rather than by mechanical linkage to a crankshaft. The fluid dynamics calculations were similar. The challenges of managing compression ratios, temperature limits, and efficiency were comparable. Hooker's expertise with centrifugal compressors proved directly applicable to early jet engines, which used centrifugal rather than axial compressor designs. But it was the Merlin work that defined Hooker's contribution to the war effort. In 1946, after the war ended, the Royal Aeronautical Society awarded Hooker its Silver Medal for his development of the two-stage supercharger. The citation noted that his work had materially affected the course of the war in the air. This was not hyperbole. Without the performance advantages the two-stage Merlin provided, the Spitfire would have remained outclassed by German fighters through 1942 and 1943. The Mustang would have been relegated to low-altitude roles where its range advantages were less valuable. The long-range escort mission that became the Mustang's defining role would have been impossible without an engine that could deliver power at the altitudes where bombers operated and fighters fought. The strategic bombing campaign that destroyed German industrial capacity would have suffered unsustainable losses without effective fighter escort. The air superiority that Allied forces achieved by mid-1944, which made the Normandy invasion possible and supported the advance across France and into Germany, depended on having fighters that could dominate German opponents in every performance category. Hooker's later career demonstrated his continued engineering excellence. He became chief engineer at Rolls-Royce's jet engine division, then moved to Bristol Aero Engines, where he developed the Olympus turbojet that powered the Vulcan bomber and later the Concorde supersonic transport. He designed the Pegasus vectored thrust turbofan used in the Harrier jump jet. In 1971, at age 63, he came out of retirement to rescue Rolls-Royce from bankruptcy following problems with the RB211 engine. His leadership saved the company and established the foundation for modern Rolls-Royce jet engines. He was knighted in 1974 for his contributions to aerospace engineering. His autobiography, Not Much of an Engineer, published in 1984, became essential reading for anyone interested in also aircraft engine development. He died on May 24, 1984, at age 76, having spent nearly 50 years advancing the state of aircraft propulsion technology. But for the pilots who flew Merlin-powered aircraft during World War II, Hooker would always be remembered as the man whose mathematics transformed what was possible in the sky. Colonel Clarence Bud Anderson, who flew P-51 Mustangs with the 357th Fighter Group and achieved 16 1/4 confirmed victories, wrote in his memoirs that the Mustang went like hell because the Merlin had great gobs of power and was equally at home, high or low, thanks to its two-stage, two-speed supercharger. That casual reference to the two-stage supercharger contained within it the story of Hooker's achievement. The great gobs of power Anderson experienced were the product of compression ratios calculated to 5 decimal places, of impeller blade angles optimized through complex fluid dynamics equations, of intercooler designs that balanced heat transfer efficiency against weight and space constraints. The ability to be equally at home, high or low, reflected the two-speed supercharger drive that Hooker had specified, allowing the engine to optimize performance for different altitude bands. The story of the Merlin Mustang is often told as a romance between an airframe and an engine, and there is truth to that narrative. North American aviation's designers, led by Edgar Schmude and Raymond Rice, created an airframe with exceptional aerodynamic efficiency, the laminar flow wing, the low-drag cooling system, the clean fuselage lines, all contributed to performance that exceeded contemporary designs. Rolls-Royce's Merlin engine, refined through years of development, provided power and reliability that made it the Allied standard for high-performance aircraft. But the transformation that made the Mustang truly exceptional came from specific technical decisions made by a mathematician who approached supercharger design as a problem in fluid dynamics, rather than as traditional mechanical engineering. Hooker's two-stage compression system, with its liquid-cooled intercooler and two-speed drive, was not an obvious solution. It required calculations that most engineers of that era could not perform. It required confidence that the mathematics would prove correct, even when conventional wisdom suggested otherwise. The vindication came in October 1942, when Captain Shepard flew the first Mustang X from Hucknall and discovered that the aircraft performed exactly as Hooker's calculations had predicted. It came in November 1942, when Bob Chilton flew the XP-51B and achieved the same 441 miles per hour at altitude that the British prototypes had demonstrated. It came in every combat mission where Mustang pilots found they could outclimb, outrun, and outfight opponents who should have had the advantage of defensive position and familiarity with the battle space. The German prisoners of war who witnessed American industrial might experience a psychological transformation when they understood the material abundance that democracy had created. The Mustang pilots who learned Lindbergh's fuel management techniques gained operational range that multiplied their effectiveness, and the Allied air crews who flew with Merlin engines, whether in Mustangs or Spitfires or Lancasters, benefited from engineering that pushed the limits of what piston-engine aircraft could achieve. All three stories share a common thread. Technical knowledge, properly applied, changes what is possible. Industrial capacity without engineering excellence produces quantity without quality. Engineering excellence without proper fuel produces designs that cannot reach their potential. But when knowledge, resources, and application align, the results can be decisive. Stanley Hooker's two-stage supercharger represented knowledge properly applied. His mathematical understanding of fluid dynamics allowed him to design compression systems that other engineers considered too complex to be practical. His willingness to challenge conventional wisdom about air-to-air versus air-to-liquid intercooling led to solutions that fit within the constraints of single-seat fighter design. His attention to the details of impeller geometry, diffuser angles, and intercooler passage sizing ensured that the theoretical advantages translated into actual performance. The pilots who flew the results of his work rarely knew his name. They understood that the Merlin engine was powerful and reliable. They appreciated that their Mustangs could escort bombers to Berlin and back, could fight at 30,000 feet, could outperform German fighters in virtually every engagement. They knew their aircraft gave them advantages that saved their lives and allowed them to complete their missions. But the mathematical foundations of those advantages remained invisible, as they should. Good engineering disappears into the background. Pilots should not need to understand compression ratios or intercooler efficiency to use their aircraft effectively. The fact that the Merlin's two-stage supercharger worked reliably, delivered consistent performance, and required no special knowledge from operators was evidence of successful design. Hooker's achievement was creating complexity that presented itself as simplicity. The war in Europe ended on May 8, 1945, with Germany's unconditional surrender. By that date, Allied air forces had achieved absolute air supremacy. The Luftwaffe had effectively ceased to exist as a coherent fighting force. The few remaining German aircraft rarely flew due to fuel shortages, pilot shortages, and the overwhelming presence of Allied fighters that made any flight suicidal. The final missions flown by Mustang pilots in April and May 1945 often encountered no aerial opposition. German fighters stayed on the ground. When they did fly, they were usually destroyed quickly by American pilots who had accumulated hundreds of hours of combat experience flying aircraft that were technically superior in every measurable category. The air war's outcome had been determined months earlier. The final weeks were merely the working out of inevitable consequences. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.